When we try to simulate molecules at the quantum level, we immediately hit a mathematical wall. The electrons are in constant motion, and because they repel one another, the movement of every single electron is instantly influenced by the position of every other electron in the system. For a molecule of any useful size, the exact electronic Schrödinger equation becomes a chaotic web of interacting variables, impossible to solve exactly. This diagram illustrates the core roadblock. Tracking instantaneous repulsion requires calculating every interaction vector simultaneously. To bypass this, Hartree Fock sacrifices the exact tracking of individual particles, replacing it with an average field. Instead of dodging each specific neighbor, each electron is treated as moving independently within a static, smoothed-out electrostatic cloud generated by all the other electrons combined. We trade absolute physical truth for a framework that computers can calculate, establishing the baseline mathematical architecture for modern chemical simulation. Even within this average field compromise, the simulation must respect the rules of reality. Electrons are fermions, bound by the Pauli exclusion principle. In quantum mechanics, this requires the total wave function to be perfectly antisymmetric. If two electrons swap coordinates, the sign of the entire wave function must flip. To enforce this mathematically, Hartree Fock uses the Slater determinant. It places each electron into a spin orbital, defining its space and spin. If two electrons share a spin orbital, two columns become identical, evaluating to zero, an impossible state. The Slater determinant functions as an automated mathematical bouncer. No matter how the simulation adjusts, it will never yield a result violating the Pauli principle. With the rules enforced, the operational goal of Hartree Fock is to adjust these spin orbitals until the total electronic energy reaches its lowest possible point, adhering to the variational principle. The mathematical engine computing this energy landscape is the Fock operator, mapped out here. It starts with the one-electron energy, which accounts for the kinetic energy of the electrons in motion and their physical attraction to the positively charged atomic nuclei. Added to that is the Coulomb energy. This is the classical light calculation of the average electrostatic repulsion each electron feels from the surrounding cloud. Finally, the equation subtracts the exchange energy. This term has no equivalent in classical physics. It exists entirely to account for the energy shift caused by the quantum antisymmetry we enforced with the Slater determinant. The Fock operator is a distinct hybrid. It maps the total energy of the molecule by blending standard classical electrostatic forces with strict purely quantum mechanical corrections. But solving this operator creates a computational paradox. The Fock operator calculates the energy using the orbitals, but you need the operator to find the correct shape of those orbitals in the first place. To break this circular dependency, we use an iterative algorithm called the self-consistent field, or SCF cycle, detailed in this flowchart. We bypass the paradox by guessing a set of initial orbitals, which gives the computer enough data to build the very first average field. The operator uses that field to solve for new, slightly better orbitals. We then take those new orbitals, rebuild the field, calculate the energy again, and check if the results match the previous step. This loop runs continuously until the orbitals we put into the equation exactly match the orbitals we get out. When the field no longer changes, the results converge. Before initiating this cycle, we must tell the system how to allocate spin. As this table shows, we select restricted Hartree Fock for closed-shell molecules where all electrons are paired, or unrestricted Hartree Fock to allow flexibility for unpaired electrons in open-shell systems. The paradox is resolved not through exact calculus, but by forcing the simulated physics to iteratively stabilize until it settles into its lowest energy state. While the Hartree Fock equations are mathematically elegant in continuous three-dimensional space, computers are highly inefficient at solving continuous differential equations. To execute this in software, we expand the unknown complex molecular orbitals into a linear combination of known distinct mathematical shapes, called basis functions. This graphic illustrates the critical step. It translates continuous physics equations into discrete matrix algebra, yielding the Roothaan equations. The software solves Fc equals Sc epsilon. F is the Fock matrix. C contains orbital coefficients, S calculates spatial overlap, and epsilon stores final orbital energies. Populating these matrices requires a practical compromise, shown in this graph comparing Slater-type orbitals with Gaussian-type orbitals. Gaussians, the rounded yellow dashed line, are less physically accurate near the atomic nucleus. However, their specific mathematical properties allow computers to integrate them exponentially faster, making the millions of calculations required for an SCF cycle viable. Without the Roothaan matrix translation and the speed of Gaussian functions, routine quantum chemistry would be too computationally expensive to exist. The basis functions act as the vocabulary we use to describe the electronic wave function. If the vocabulary is too small, the software cannot accurately describe the shape of the molecule. Starting with rigid minimal sets, providing basic spheres, we expand accuracy using split valence sets, allowing outer electrons to adjust independently. Polarization functions add complex shapes to accurately model bent bonds, while diffuse functions provide massive boundaries to track electrons far from the nucleus. Increasing the size of the basis set reduces basis error, pushing the calculated energy closer to the true Hartree Fock limit. But a perfect mathematical vocabulary cannot fix a flaw in the physics itself. This diagram highlights the method's blind spot, electron correlation. Relying on an average field approximation, Hartree Fock completely misses the instant-by-instant dodging of individual electrons. It serves not as the final answer, but as the necessary foundation, providing optimized orbitals that advanced post-Hartree Fock methods build upon.